Hello class, what we're covering now is an extension onto waves. Now we're getting into a specific type of wave, the harmonic wave, or a harmonic wave, a standing wave, where essentially we have two fixed points along a path and a wave can travel between those 2 points, but those points can't move up and down. But the rest of the material can. What we're doing here is being asked to draw the sixth harmonic standing wave, or F sub 6, traveling through a string where these 2 points are fixed. Well, a traveling wave or a standing wave, essentially it has points where it looks like there are points along that wave that aren't moving, where the rest of the string, as that wave is traveling through it, there are going to be parts where that string is pushed up and down, up and down, up and down, and then that wave will then reach a fixed point and start traveling in the opposite direction, up and down, up and down, up and down. And there are going to be points where it looks like that string isn't moving at all. And there are going to be points where the string is basically warping up and down as that wave is traveling through the string. Well, for the sixth harmonic standing wave, that 6 just means that you're going to have 6 antinodes and you're going to have 6 plus 1 nodes in this problem. A node is a point where the string doesn't cause the wave to move up and down. It's basically a fixed point. So node 1, 2, 3, 4, 5, 6, and 7. An antinode is where you have a maximum change in amplitude. So as this string is being pushed up and down, we have one antinode here. We have a second here, a third here, a fourth here, a fifth here, and a sixth here. So anytime you have a material that a wave can travel through, and that material has two fixed points that can't move up and down, what you are going to have is a standing wave where the number of antinodes equals our little frequency number or our subscript number, or the type of harmonic wave that we have. So the sixth harmonic standing wave, that sixth or that 6 indicates the number of antinodes, the number of maximum points of maximum amplitude change, and it has 6 plus 1, whatever this number is, plus 1 antinodes, or the number of fixed points where the string isn't being pushed up or down, but the position is staying fixed, which includes our 2 fixed points plus additional points within. So if you're told to draw the sixth harmonic wave, basically just go up, down, up, down, up, down. In other words, have at least 3 crests and 3 valleys. That adds up to 6. If you were told to draw the fifth harmonic wave, then you would draw 3 crests and 2 valleys, or 3 valleys and 2 crests. Think of it like that. And then see if you have the correct number of nodes and antinodes. So, let's see. Note the nodes are where there is node change in amplitude as the wave moves back and forth. As that wave is moving left and right, it's pushing the string up and down, essentially. Antinodes are where there is a maximum change in amplitude, so a maximum change in how that string, that physical material, is being changed as the standing wave is traveling through it. It's called a standing wave because it makes it look like the material is staying still, where basically parts of it are just moving up and down, and it's not obvious that the energy is traveling left and right. But so, first problem, it asks how many nodes and antinodes. If we're dealing with the sixth harmonic wave, we have 6 plus 1 nodes, and we have 6 antinodes. So that's part's done, and we just drew it here. For your worksheet or test, you can show the wave motion in one direction, so moving from right. So from this point to this point, up, down, up, down, up, down. I'm showing the backwards direction as well, just because it's a way of showing very clearly where the antinodes are, where the string has a maximum moving up and a maximum moving down, a maximum change in amplitude. But you don't have to show the backwards direction if you don't want to. If you do, just use a dashed line to make it very clear that the solid line is in one direction as energy is moving in one direction, and the dashed line is energy in the wave moving in the opposite direction before repeating. But like with any wave, we have parameters that we can calculate for it. And in this scenario, if the total length L of a string is 90 meters and the speed of the wave V is 800 meters per second, determine the wavelength lambda, the frequency F, and the period T of this wave. Well, depending on the harmonic frequency we're working with, F sub n, we can calculate wavelength through the following equation. That harmonic number n divided by 2 and all that multiplied by the wavelength equals the total length of our material. So rearranging this by multiplying 2 over n to the other side, the wavelength lambda equals 2 times the maximum length of the string that the wave is traveling through divided by n, the harmonic number. We were told at the start we were working with the sixth harmonic wave, so the harmonic number n is just 6. And we were told that the string had a length of 90 meters. So 2 times the length divided by the harmonic number, that gets us to 30. And since length is in units of meters, wavelength in this case would also be meters. As far as frequency goes, our equation for this wave is wavelength times frequency equals wave speed. So rearranging to solve for F, frequency is the wave speed divided by wavelength. We're told that the wave speed is 800 meters per second, and we just calculated the wavelength to be 30 meters. So if we take 800 divided by 30, we get 26.6 repeats, a bar over that 0.6 saying that's a infinite number 6 after the decimal. You could instead leave it as just a simplified fraction, so 800 over 30, that's the same thing as 80 over 3. Either answer you write, just remember that the units for frequency are going to be hertz. If we're taking meters per second divided by meters, the unit would be 1 over seconds, which we just replaced with the placeholder hertz instead. And then the period, the amount of time it takes for that wave to do one full oscillation from up to down and back, that is going to be t, the period, and that equals the inverse of the frequency, so 1 over f. So 1 over 26.6 repeats, basically add 5 sixths after the decimal if that's a repeating decimal, just to avoid rounding errors. Or if you left it as a fraction, flip it, and we have 3 over 80, and whether you do one or the other, what you are going to get is 0.0375, and once you take the inverse of hertz, you are back in the time dimension, so we are now in units of seconds. Interestingly, It is possible to determine the tension force F subscript T or F sub T within a string under this above scenario, where a harmonic wave is traveling through that string. The necessary information would be knowledge of the speed, so V, the mass of the string that the wave is traveling through, M, and the length of the string, L. With the information given, determine the tension force of the above string if it has a mass of 0.9 kilograms. Well, our main equation here is that the wave speed is equal to the square roots of the tension force times the length of the string divided by the mass of the string. If we rearrange this, basically squaring both sides so that we have wave speed squared, then multiply mass to the other side and divide by length to the other side, we can determine the tension force that that string is experiencing due to the standing wave that is oscillating in that string as the tension force Ft equaling the wave speed squared times the mass divided by the length of the string the wave is traveling through. As far as making sure that the units check out, we have for wave speed meters per second, and that's being squared, and mass is in kilograms, and length is in meters. So what we are left with next is kilograms times meters squared divided by meters seconds squared. The meters, a meter in the numerator cancels out with the meter in the denominator, so we're left with kilograms times meters per second squared, which is the same thing as mass times acceleration. Acceleration being meters per second squared. And mass times acceleration is the unit Newton, and that's how we know we're working with a true force. To actually answer the problem though, Ft, or the tension force of the string, is the wave speed that we were told in the prior problem, 800 meters per second, and we're going to square that, and we're going to then multiply it by the mass in kilograms, which we're told was 0.9 kilograms, and then we'll divide it by the length, which again in the prior problem, in the prior paragraph or sentence, we were told that the length was 90 meters. So that's how we got all these numbers here. 800 meters per second squared times 0.9 kilograms divided by 90 meters. And that gets us 6,400 newtons. In any case, this covers our lesson topic for this week, or our worksheet, our practice worksheet for this week, basically concluding our discussion on wave properties. That's part of our physics for the industry trades, or essentially a very general education level physics class at the undergraduate level, but general education level. In any case, glad to have you all. Just to see that notification button change a color, you're welcome to subscribe to the channel and hit the like button. At this point, there should have been a rainbow effect if YouTube still does that. But no matter what, glad to have you all in this class and wish you all the best. And peace.